So this session is mainly related to the doubts related to topic 2, which is about the mass spectrometer and ionization energy. The first one is question 11D. So this is 11D, the log of fourth ionization energy of 6 elements shown. Means we took a logarithm, we took the log value, and we got the ionization energies are shown. We have to plot a graph. So how we will plot a graph using these values? We will first select a scale for the graph. For the 4 elements. So you can see the minimum value is 3.8 and the maximum 3.87 and the maximum value is 4. And on we have the element. So what are the elements? We have element oxygen is there, then fluorine is there, neon is there, and so on. So how we can plot this result? Like oxygen is there, fluorine is there, neon is there, sodium is there. It's not given magnesium. Or we can start oxygen, fluorine, neon, sodium, magnesium, and aluminum. And for y-axis, we can select a scale because the minimum value is 3.87. So we can start from 3.8, then this will be 3.9, or we can extend our scale 10 boxes equals to, so this will be 3.9, this will be 4.0, and here it will be 4.1. So for oxygen it is 3.87. So 3.87 means because two boxes are equal to 0.01, so this will be 3.85, 86 and 87 will be 4 boxes. This will be 3.87. Fluorine is 3.92, so after 3.9, 3.91 will be 2 boxes, and then 3.92 will be 4 boxes. 3.97 neon, sodium is not there, so neon is shown 3.97. So this will be 3.95, 96, and then 97. Then we have magnesium, that is 4.08. So 4.08, so 4.02, sorry. So this will be 4.01 and then 4.02. And aluminum is there, which is 4.06. So 4.505 is this, and 4.06 will be 2 boxes after that. So you can see it will form when we join these points. It will be a straight line, which shows the consecutive elements. The trend is there in their increase or change in ionization energy. So this is a graph which we have to plot. The next part is estimate the ionization, the fourth ionization of sodium. So we have to estimate the fourth ionization energy of sodium first. what we have to do, because this is a log of ionization, this is not ionization, this is logarithm of ionization. So using the graph, first we will identify, we will predict. So as you can see, sodium is here. The neon, it was supposed to be at this point. So sodium is, this is sodium, so we'll draw a line from sodium and work out the value. It's coming out as 3.9, and there are 6 boxes, 1 2 3, so 3.93, because 2 boxes representing 0.01, so 3.93. But 3.93 is log, so log of ionization energy is equals to 3.93. But we want to remove the log, we need ionization. So ionization energy will be anti-log of, so what is, because this is a log of base 10, so when we take an anti-log, you will press shift and anti-log, so it means 10 raised to power 3.93. So what will be the answer when you use 10 raised to power 3.93? So it is, when you check the trend, the exact numbers, so log of 3.93, this was sodium, so it is following a trend. So you will get the answer for this. Is it clear? The value, the range, the final answer should be from 9,9544 to 10,000. But because the graph, this is approximation, I did not use the exact graph. So when you're using an exact graph, your answer will be closer to the accurate value. Is it clear, this doubt? Then we have another doubt. First, this was 11. Then after 11, 25C. 25C. In the recent year, a particular linen, linen cloth was shown using the mass spectrometry to have been made from flax grown in early 14th century. Suggests how a mass spectrometer can be used to estimate the age of the cloth. So how this mass spectrometer can be used to estimate the age of the cloth? Because using the mass spectrometer, what we can do, we can work out the amount of the sample, and here its answer is related to two things. One, it is related to the physics, like a concept of the half-life, So using the mass spectrometer, what we will do, because we know carbon having an isotope which is carbon 14, that is radioactive. So what we will do using a mass spectrometer, we will compare amount of carbon 14, the radioactive sample, the radioactive material carbon 14, or what is the amount of carbon 14 is there in the sample which we have. So using this and a half-life, like example, say we have, as I mentioned, in recent years, a particular linen cloth was shown using a mass spectrometry to have been made from a flax which is grown in the 14th century. So how a mass spectrometry can be used to estimate the age of the cloth? So how we can use it to identify the age of the cloth? So basically what we will do, we'll compare amount of carbon 14 in the sample of the cloth and using the half-life, like example, if originally the cloth example is having only 2 grams of carbon 14 and the total mass of the substance example 10 grams, 10 gram substance contain, or we can compare the ratio between carbon 12 or carbon 14. So what happened, the carbon 14 will decrease with the passage of the time. So we will compare with the total mass how much carbon 14 is there, and what will be our assumption. Our assumption is that because when the plants are growing, they're continuously taking in carbon dioxide, so the amount of carbon 14 is not changing, more or less it remains same. But once the plants die, now the carbon 14 which is there, that is the amount of carbon 14 start to decrease. So what we will consider, we'll consider the half-life, like we assume, like if the original sample was 12 gram and now we have 2 grams. So how many half-lives are there? So 10 gram changes into 5 gram, then 5 gram changes into 2.5. So example, we have 2.5 gram of carbon 12. So how many half-lives are there? The half-lives, 2 half-lives are there, and half-life of carbon 14 is 4,500 years. So we can say, or we can estimate that this sample is about 9,000 years old. So simple way, what we will do using a mass spectrometer, we'll identify the percentage of carbon 14 and then we will compare with a half-life of carbon 14, and using the half-life we can work out how much time it will take to decay, and using this we can estimate the age of this cloth which was believed to belong to 14th century. Is it clear, the idea or the concept? So first part is related to mass spectrometer and the second part is related to the physics in which we work out the half-life and identify the age of the plant. Next question 28. 28 part D1. So mark on energy level diagram with an arrow transition that represent the ionization. Ionization means like when you have an atom, electrons are there. So the term ionization means removal of electron from the atom. If we remove the electron from the atom, electron go outside the atom, we call that as ionization. So every element is having 7 shells, but occupied, the number of occupied shells are different, but every element is having 7 shells, as we know. So there's a K shell, L, M, N, O, P, and then Q shell. So every element is having 7 shells. In case of hydrogen, it is having 1 proton and 1 electron. So what is the meaning of ionization for hydrogen? It is a removal of electron from the first shell to outside the atom, or outside the atom, what we call that? We call that as infinity, like undetermined space. So if we want to draw an arrow to show the ionization of hydrogen, so infinity, as you can see here, this infinity sign, what does it mean? It means it is outside the atom. So how we represent the ionization? Using an arrow. So electron in hydrogen is there in the first shell, and it go out from the atom. So this will be the ionization of hydrogen. Is it clear, this part? This was 28D1. Next is 36C. 36 part C. The element C2, 36 part C2. In a sample rubidium isotope, it is 85 with abundance 2.5 times greater than rubidium 87. So you have two isotopes of rubidium. Rubidium 85 is there, and rubidium 87 is there. And this rubidium 85 is 2.5 times greater. So when we compare the ratio, this is 2.5 times compared to rubidium 87. So ratio is 2.5 is to 1. If we have the ratio, we can also work out the average atomic mass or relative atomic mass. The ratio, which is 2.5, multiplied by the mass, which is 85, plus the ratio, which is 1, multiplied by the mass, which is 87, and divided by the total sum of the ratio. So 2.5 plus 1, that is equals to 3.5. So relative atomic mass, we can just substitute these values and we'll get the relative atomic mass of this rubidium. Is it clear, this part? That was also a doubt. So when ratios are given, you can just simply use this technique to work out the average mass of the isotope. So this was 36C, then 37A is there, 37A2, 37A2. Give two reasons why. Give two reasons why the second ionization of magnesium is greater than the first ionization of magnesium. Like, the first ionization means energy required to remove electron from neutral gaseous atom. That is first ionization. The second ionization, already electron is being removed. So we supply energy and we have to make magnesium plus 2 charge. So they are asking why this enthalpy change is higher compared to the first ionization energy. When you check the shell, first thing for magnesium, because here you are removing the electron from magnesium atom. Magnesium atom is having 3 shells. But magnesium, so when you compare this, when we are removing the electron from magnesium atoms, the first shell it will have 2, second shell it is having 8, and third shell it is having 2. So when we remove, or we want to remove this electron, there are 11 protons, there are 12 protons, and there are 12 electrons. So there is a balance between the number of proton and number of electrons. But when we want to remove the electron from magnesium, which is already a magnesium ion, which is already a charge, so you can clearly see that this magnesium ion, first shell it will have 2 electrons, the second shell it will have 8 electrons, and the third shell it will have only 1 electron. But when you compare the size of magnesium plus 1 charge with magnesium atom, so magnesium plus 1 charge or magnesium ion will be smaller in size as compared to magnesium atom. So two reasons we have to give why the second ionization energy is higher. So first thing, the magnesium ion is smaller as compared to magnesium atom. And the second thing, because here what is happening, we are removing the electron from neutral atom, but here magnesium is already charged. So when we try to remove this electron out, this electron will experience the attraction from the positive charge. That is why it will be difficult to remove the second electron from magnesium atom. So first thing, magnesium ion is smaller in size, and electron will be closer. That is one thing. And the second thing, the magnesium plus 2 ion, magnesium plus 1 is positive charge or positively charged, which attract the electron which we are trying to remove. So the electron here, because what happened when we remove electron from magnesium atom, originally there is no attraction here, because the net there is attraction but not towards it, but this is already charged, so it will be difficult to remove this electron out. Is it clear the reason? So magnesium ion is being removed from a positive ion, the electron is removed from the positive ion, so it is having a stronger attraction. Or you can also say here the proton to electron ratio, so there are 12 protons and 12 electrons. But in this case, there are 12 protons and 11 electrons. That's why each electron will experience greater attractive force. Is it clear the reason? Then 37A, this was 37A2, and then we have 39. A sample of oxygen contain isotopes 16, 17 and 18. How many peaks will be there in oxygen molecule? Basically, this is oxygen molecule O2. So how many peaks? This is not oxygen plus 2 charge, it means oxygen molecule with a charge plus 1. So what are the possibilities? Then if in oxygen molecule, maybe both of them are 16, maybe one of them is 16, another one is 17, maybe one is 16, another one is 18, maybe it is 17 and 18, or maybe it is 18 and 18. So if it is 16 and 16, so you'll get a peak at 32. If it is 16 and 17, you will get a peak at 33. If it is 16 and 18, you will get a peak at 34. If it is 17 and 18, you will get a peak at 35. And if it is 18 and 18, you will get a peak at 36. So these are the possible peaks which you may have if you have oxygen molecule which is having a net charge of plus 1. So it will be B, or 5 peaks will be there. Because this oxygen molecule might have a combination 16-16, 16-17, 16-18, 17-18, or 18-18. So this was question 39. Then it is 43B, 1, 2, and 5. 43. This is question 43. The doubts are B1, B2, and B5. B1. Okay. The successive ionization energies of potassium are shown, as you can see here. Estimate the first ionization energy and the 19th, estimate the first and the 19th ionization energy. Use the data from a graph and your calculator. So what you can do, it is log of ionization energy. So when it is a log of ionization energy, example, this value, because there are no numbers in between that, so you have to estimate the number. So example, this first number, the first ionization energy for this, between 2 and 2.5, so means each is representing 0.5. So 2.5 to 3, so what I can estimate, it is like 2.6, because if it was at the center, then it will be 2.75. So you just estimate that this value might be 2.6. So log of ionization energy is 2.6. But we need ionization energy, so we have to take antilog. This is a log of base 10. So when we take antilog, it means 10 raised to power 2.6. On your calculator, you just press a shift and log is there. Press that same button. It will give you antilog of 2.6. So what will be the antilog of 2.6? Example, it is 398 and the unit will be kilojoule per mole. That is the first ionization. What about the 19th ionization? So 398.1, it will be kilojoule per mole. And what about the 19th ionization? So it is like 5.6 and 5, it look like 5.7. So what we'll do, we'll take again the log of ionization energy is 5.7. So what we'll take anti-log, so ionization energy will be 10 to the power 5.7. What is the answer for 10 to the power 5.7? It is 501,000. It's about 50,000. No, 501,000. Okay, 500 is the difference. So 501,000 kilojoule per mole will be the ionization energy. the 19th ionization energy. So just you have to take anti-log and you will get the result. Then it was second part, explain why the logarithm of ionization energy is used. So what is the reason why logarithm is used? You can clearly see when we work out the first ionization energy, what was the answer? The answer was about 398. The first ionization energy was 398. The 19th ionization energy is about 500 or 501,000. So you can see between the first value and the last value, there is a big difference, and it will be difficult to plot these on the same scale. So when you plot a graph, you want the scale to be same. So whenever the values are having a greater difference between them, instead of plotting the values directly, what we take the log of the values, because the log will reduce the value so that it can fit into the graph. So when the graph, the variation or the difference between the smallest and the biggest, largest value is too high, in that case we do not directly plot the graph for the values, we plot a graph for logarithm value. So you can mention here there's a greater range or a large range, that's why it will be difficult to plot them on the same grid. So we take a logarithm or a log which reduces the interval between the values or reduces the range. Then B5, explain each of three sharp rises, and you should include the detail of the subshell. So it's of 3 marks. The three sharp rises, when you write the electronic configuration, it's better you write the electronic configuration. So it is 1s2, 2s2, 2p6, 3s2, 3p6, and this will be 4s1. So 19 electrons are there. So when we remove the first electron, this is removed from 4s. This is 3p, 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 1, 2, 3, 4, 5, 6, 3p, and then 3s, 3s, and then 2s, 2p, 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 and then 2s, 2s, and then 1s, 1s. This is how electrons are being removed. So why there are three sharp rises? For the potassium, so first one is due to the electron is removed from the outer shell, which is far away from the nucleus. So when the shell changes, so why there is a difference in the ionization energy for the first and the second? That is due to the change in subshell. And when the subshell changes, the 3p subshell will be closer as compared to 4s. That is why there is a change. And the second sharp rise, why there is a second sharp rise? Because again there is a change from 3s to 3p, and the same reason is there, that electron is removed from 2p, which is completely filled, so it need more energy to remove electron. That's why there is also a sharp rise. And the third one, the rise is there for 1s and 2s. Why? Because again there is a change of orbital, 1s and 2s. The third sharp rise is there because electron is removed from the first shell, which is closer to the nucleus. So for you will mention the name of shell and mention the reason, because the shell 3p is closer and it is completely filled. Same thing, the second one is between 3s and 2p, which is closer, 2p is closer and it is completely filled. And the last one is between 2s and 1s, because 2s is much closer to the nucleus and it is completely filled. That's why it needs the highest energy to remove the electron from the outer shell. Is it clear, this question? And then we have question 45. So in this one, the five successive ionization energy of element are shown. If you want to determine the group number or the period number, what you have to do, you have to check the jumps. So 590, 1100, it is approximately double. But when you compare 1100 with the next value, which is 4900, so this is a big jump, because this is approximately double, but this is a big jump. So it means how many electrons are there in the last shell, that it is having 2 electron in the last shell. So if element is having 2 electron in the last shell, it means the valency, that more likely when it react with chlorine it will lose 2 electron. That is why B is the right answer for this. Is it clear? So we have to check the jump, the difference, 490, 1100, so it is this approximately same. Then you can see a big difference is there in these two values when you subtract. So big difference means the shell changes, and when shell changes, it means this was the number of electron in the last shell, so there were 2 electron in the last shell. That's why it will form an ion of plus 2. So I'll share another link and continue this discussion.